Imagine a computer, not the kind on your desk or the one in your phone. This computer thinks differently. It learns like you do. It is inspired by the brain. This is neuromorphic computing, a truly revolutionary idea. It promises a new age for artificial intelligence and for all of computation. Why is this so important now? Artificial intelligence is growing fast. It demands incredible power. Our current computers struggle. They consume vast energy. They heat up our world. We need a smarter path. Neuromorphic computing offers this. Efficiency is its guiding star, a new dawn for intelligent machines, our quest for true AI. It often leads us to nature. The human brain is a masterpiece, an intricate living network, billions of tiny neurons firing, connecting, learning always. It processes complex information. It uses very little power. Can we build something similar? That is the grand challenge. This journey will explore it. The human brain. It is our universe within. It holds our thoughts, our dreams. It learns from every experience. It perceives the world around us, seeing faces, hearing music. All this with incredible efficiency, using just a little bit of power, about the same as a dim light bulb. A marvel of biological engineering. Neuromorphic chips try to copy this. They aim to emulate the brain, its structure and its functions. Engineers build artificial neurons. They create artificial synapses. These are the connections between the tiny neuron cells. Information flows through them, not in a rigid, fixed way, but dynamically, like life itself. Traditional computers are very different. They follow a classic design called the von Neumann architecture. The processor is one part. The memory is another, separate part. Data must travel constantly, back and forth between them. This creates a traffic jam, a bottleneck slowing things down. It also wastes energy. Neuromorphic systems change this. They merge processing and memory, much like our brains do. Neurons themselves hold data and they compute with it. This radically reduces data movement. Information is processed locally. This approach is faster and far more energy efficient. A cosmic shift in design. A brain-inspired architecture. This is the very heart of every neuromorphic system. Think of countless tiny processors. These are the artificial neurons. They are massively interconnected by artificial synapses, the wires, forming vast parallel networks like constellations of thinking stars ready to light up with information. Event-driven processing is key. This is another vital concept, unlike standard computer chips which run on a constant clock. Neuromorphic neurons are different. They only activate when needed. When they receive a signal, an event or a spike, only active neurons consume power. The rest remain quiet, waiting. Imagine you are in a library, a vast, silent, dark space. Suddenly someone whispers your name. Only then do you turn. Only then do you react. Your brain processes that event. Neuromorphic chips work this way, not with constant, noisy chatter, but with meaningful, sparse signals. This saves enormous energy. These tiny electrical spikes, they are the language of the chip. They carry all the information. The timing of these spikes, when they arrive, how often, the patterns they form together. All this creates a neural code, a rich tapestry of data woven by the firing neurons. The system learns to interpret this. Section 4. Efficiency and adaptation. The neuromorphic edge. Adaptive learning is truly crucial. Neuromorphic systems are not static. They are designed to learn. They can change their internal connections. The artificial synapses can adapt. Some connections grow stronger if they are used often. Others might grow weaker if they are rarely active. This mirrors brain plasticity. Our own brains constantly rewire as we learn new information, as we master new skills or form lasting memories. Neuromorphic chips strive for this, to learn from new data, to adapt to changing conditions, all without explicit reprogramming. This is a powerful feature. Then there is energy efficiency. This is a monumental advantage. Our biological brain is a champion. It performs amazing computations using only about 20 watts. Your laptop uses much more. Data centers consume gigawatts. Neuromorphic systems aim low. They sip power, not gulp it. This remarkable energy saving comes from several factors. The event-driven processing helps. Only active parts use power. The parallel architecture helps too. Tasks are spread out efficiently. Memory and processing are close. This frugality is vital for AI, especially for devices at the edge. Small, portable, and smart. Section 5. Silicon Mines. Pioneering neuromorphic processors. Scientists and engineers worldwide are building silicon brains of the future. IBM's True North chip has 1 million digital neurons. It demonstrated neuromorphic hardware's potential. Intel's Loihi chip supports on-chip learning. Spinnaker from Manchester University simulates large networks of spiking neurons. It helps us understand the brain. Section 6, Real-World Impact Applications Shaping Our Future. Real-time sensory processing. Neuromorphic systems truly excel here. Imagine processing visual data or complex audio streams just like our eyes and ears do, but much faster, more efficiently than traditional computing methods. This opens new doors wide for smarter perception systems. Robotics will be transformed. Robots need to sense their world. They need to react quickly and intelligently to changes. Neuromorphic chips can serve as low-power, agile brains for these autonomous machines, making robots more aware, more capable, and more helpful in our homes and industries. Consider low-power AI devices. Think of intelligent sensors deployed in remote locations or wearable technology that learns your habits, your health needs. Medical monitoring devices too, running sophisticated AI locally, all without quickly draining their small, precious batteries. This is where efficiency shines. Brain-machine interfaces also benefit. These connect human minds to tech. Neuromorphic computing can help to better decode complex signals from the brain's own neural activity. This could aid people with disabilities. Neurological research also advances. These chips help us model brains and understand their mysteries better. The cosmos within us unfolds. Section 7, Conclusion, Charting the Course for Intelligent Hardware. Neuromorphic computing is still young, a field full of exploration, yet it holds such vast promise. It offers a new direction for the future of artificial intelligence, a way to move beyond the limitations of today's hardware. It represents a cosmic shift in how we think about computation. It draws its deep inspiration from nature's most elegant designs, the intricate, efficient brain. Its remarkable solutions for processing torrents of complex information, for learning from experience, for adapting to a dynamic world, and for conserving vital energy. Lessons from billions of years of evolution's patient work. Of course, challenges still remain on this exciting starlit journey, scaling these neuromorphic systems to even larger, more complex sizes, developing new algorithms tailored for these unique architectures, creating user-friendly software tools for programmers and researchers. The pioneering work continues daily, yet the future appears bright. Neuromorphic hardware could indeed be a cornerstone technology for unlocking truly intelligent machines, machines that might one day think, learn, and perceive more like we humans do, or perhaps in entirely new ways. The universe of computation is ever expanding before us.